point with the situations that we have is to do what we've already been talking about. Okay? Where we're looking for the different situations. And we want to decide as much as you can about it before you actually put it in the calculator. So we can put it in and find the equation of the line. We've been doing that. You can follow your steps. And we can find out what we need. Think about what this means here. We have RPMs and we have miles per hour. It says that a table showing the engine's revolutions per minute in thousands and speed. What is the X?
No, the engine.
No, it's
Engine.
First column. This is your X. This is your Y. So, if we're looking at this particular problem here, is this a direct variation situation?
yes.
Why?
No, that's right. Zero.
We don't know this.
No.
Then think about this. The engines are, if you turn your engine on and it starts going, then you start moving. So that's how you get speed. If your engine's not turning, do you have any speed?
No.
So does this make sense for this particular problem? Yes. Okay, it does make sense. So this is direct variation. Now, I will say this, when you put this in your calculator, it's going to give you a y equal. It's going to give you a y-intercept. When we look at these applications, you're going to get some points that are not exactly in a straight line. We want the line of best fit. For this situation, the line of best fit is going to be starting at 0, 0 and then increasing
To the top.
So, what I want you to do right now is put this in your calculator in stats, and we want to come up with the equation of the line.
Wait, what?
Okay, so what do we come up with for the equation of the line here?
Y equals 24.4 x plus 0.06.
So your calculator is going to give you this,
I said 6.
It's 0.4.
0.04 or something. There's a list on the board. Okay, listen. This is what your calculator tells you. But in this situation, we need to understand that we need the line of best fit. Okay, so here, since 0, 0 does make sense, what we want to use is just this part, because 0, 0 does make sense here. This is where it has to be logical. Okay, so if it said what would be the line of best fit for this, 24.4x. Now we can plot these points on our graph and see the general equation of the line, but we need to have a window that's going to work. This is another area that we've been having problems. I'm looking at X here, our RPM. Yeah, I mean we don't need to go more than 10. So if we say 0 to 10, we can count every other one. What about for Y? 50. Okay, we need to go up at least to what, 150? And so we can estimate, you could count by tens if you want to. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then 1, 2, 3, 4, 5. Actually, I think it goes to 160. You got off one there. Because then I have to be exact. Now, when you put this in your calculator window, you could put the numbers actually the low and the high for each one and see your graph. So if we plot a couple of these, I know that 0, 0 makes sense. We also can say, okay, we have 2 and 49.1, 6 and 147. I'm not going to put them all in here, but put a few. and let's see, 3.2 and 78. And so if we were to draw a line through these, that's going to go through those, but if you look at your calculator, it may not be exact. And it's okay. There may be a line that is, or a dot that's a little bit off of that. Maybe have 5.6 and 137. Maybe it's over here. The line of best fit goes through each one of those. What type of correlations does this graph have? You only have three choices: positive, negative, or none.
Positive.
We drew the line of best fit. What's our slope?
84. 84.
And what does it represent on this particular problem? Y over X. What does miles per hour represent?
The articles.
Speed per revolution. If you didn't know that was revolutions per minute, you could have looked in your, up there in your problem, it told you. So we said, what's the y-intercept? Well, the calculator gave us 0.04, but we said that 0 makes sense. And it says, what does it represent here? Well, it represents 0 speed, because if the engine's not turning, you're not getting any speed. So you have to think logically here. So if we write the equation of the line, this is where you can get confused, because the equation of the line from the calculator does have a y-intercept. But we already said why we're using 0. So if the engine's not moving, we don't have any miles per hour. So it would be direct variation. Then logically, that's what makes sense. Everybody try number 6 here. If the tachometer measures the engine's RPM, it measures 4,000, how fast is the car going? See where you're going to put that in your calculator. In our table up here, it says that they're in thousands. So if you put this in your calculator as 24.4 times 4,000, you're going to get a really big number for your miles per hour. That does not make sense. So we need to be careful and say, okay, we don't want to do the zeros here. We only want to do 4. So then it's approximately 98 miles per hour, which makes sense. This is where we have reasonableness of answers. If you look that up and you just blindly take what the calculator tells you, then you're missing something there. You need to make sure that what you did actually makes sense. Okay, so if we go to put this in, I think I already have mine listed. So remember, if you're starting fresh from your calculator, I think we've already got this. We're going to go to Stat, Edit, and make sure that you're listing them correctly. Make sure that you double check when you're doing a list, especially a long list like this. That your numbers that you have are the same measurement all the way down. What I mean by that is that where you end, you have the same numbers in L1 that you do in L2. Because when you find the equation of your line, if it says DIM mismatch, that means the dimensions are not the same, and it can't calculate if something's missing. So that's the first thing I would check if it gives you an error message. Make sure your lists are the same. Also, when you have a lot of decimals like this, I know I missed a decimal earlier. If you come out with an answer and it doesn't look like anybody else's or mine, go back and see if you've got all your decimals in the right place. So, from here, we want to get our equation of a line, doing the same steps each time, and you've got to do the variables and put it in Y. If not, it's not going to do any of the graphing for you, or the table. So if we go back to our stat, calculate for variables and Y, when you go to enter, make sure this is the only thing that's on there, because I know that there's been an issue with you go back and you accidentally hit stat again, and you go back and you fix it, this is always sitting out on your home screen. So it needs to just say linear regression, that's what we're finding, and then put it in Y1, which is what that means. If that's all it says, and you press enter, you should get your equation. Now that's a pretty messy equation. I rounded it earlier and didn't come out with the exact numbers. This is why we want to put it in Y equals, right here, because now I don't have to remember what those are. It puts the whole thing in there, and it's going to be exact numbers. We want to be as exact as possible until the end of the problem. If at the end it says round to the nearest tenth or hundredth, do so. But if everybody get this in Y equals. If you didn't, go back to this list. This doesn't change. We're doing this every time. Even when we do quadratic later, we'll just change it to 5 instead of 4. Same step. Okay, window. Back here on our problem, we can say we have the equation of our line right here, and we can estimate it 3.24 x plus 26. You can put one decimal place, but it was 0.0, so we can say that. If you want to see what the graph is doing, we need to have a window that's going to work. What makes sense for our chirps per second? What's the lowest and the highest? Okay, maybe 14 to 20. So let's go from 10 to 20. We want it as close as we can get it. We don't have to worry about drafting it on paper this time, so we're just talking about the calculator. So 10 to 20. What about for our temperature? You want from 50 to 100? Okay. I think that's what I used already, so that sounds good. So let's make sure that's in your calculator. We used 25 earlier, so let me change that to 20. You don't ever want to change your scales on your calculator. You want to leave that the way it is. But now, I can graph. You may or may not have the dots there. Okay? If you don't, it's because the stat plot's not on. We can go to here, second stat plot, make sure it's turned on. This is what we did at the beginning of the year. The reason I have them on is that I want you to see that, do the dots themselves make a straight line? No. However, it is a positive correlation, and the line of best fit that cuts right through the center is pretty close to them. A few of them are below, a few of them are above, a couple of them are pretty close to it. That's the best estimate of a line. We do this in scientific stuff all the time. Not every single point hit, but a lot of them are really close. So if we do this and we put it in there, we can see that it has a positive correlation. Okay, as temperature increases, then the chirps per minute are increasing. Then we can answer the rest of our questions on here. Same as we did before. What is slope? What is the y-intercept? If we find the ground temperature, then what are we going to do? So let's answer the rest of those. So once we get the equation of the line, I can tell that I have my slope, temperature per chirp, y-intercepts, initial temperature when we start the process, the ground temperature when it's 95 degrees, then we can put it in our equation or look at the table, come up with about 21, I think it's 21.7 or something like that. Did anybody get it exactly? What'd you get, Dana? Okay, well it should be, I think it was 21 point, I think it was actually 6 or 7, I can't remember exactly what it was. But it was an estimate. So here with the listening device, if it's 18, and we fill in, what temperature we get right here?
84.82.
Okay, so about 84 degrees Fahrenheit. So we can use our calculator to give us information, but you also have to use the situation itself to determine what different parts that you're looking for. So on the other ones, we're going to go back, use the calculator to get the equation of the line, but use the information to decide what does slope mean, what does y-intercept mean, is it direct variation, so on.